Hello and welcome back everybody to hashtag Corp Stat Chat. In this video what we're going to be doing is talking about normal distributions. So up until this point we've been talking about discrete data using our Poisson distributions, our geometric distributions, and our binomial distributions. But what we're going to do is break away from discrete data and start talking about continuous data, because continuous is really what happens in life, right? We're talking about time here, intervals that span volume and area, distance, all those things. We can find it to be a continuous nature. So what we're going to do is we're going to talk about this normal curve, or this bell-shaped curve, and we're going to expand upon those ideas. So enjoy the video, and remember to like and subscribe. All right, let's start talking about Chapter 6 here, normal distributions. This is what it looks like. We're going to be talking about the area underneath that curve. That represents the probability. Okay, so in Chapter 6, we're going to start off with Section 6.1, which is graphs of the normal probability distribution, which is that. And we are going to study what the normal curve is, and we're also going to summarize its important properties. So there's four main properties that we're going to talk about, which is going to lead into applying the empirical rule to solve real-world problems. So let's get started with what discrete is versus continuous. We're going to move from this discrete idea the whole way to continuous, because that's where the direction we're heading. Continuous more accurately represents the world that we live in, so that's what we want to move to. However, in practice, many data sets that we collect consist of continuous measurements. So time, weight, averages, whatever it is, usually is going to be dependent upon a continuum or an interval, which is continuous. Okay, a discrete probability distribution, just as a review. You see a graph here on your left. You can see that each individual data point has its own value, so its own corresponding probability that we can calculate. But when we consider binomial, geometric, and Poisson distributions, we saw that the probability distributions were calculated for each possible discrete value. For every single discrete value, we had a probability. Now, what if we don't have individual values? What if we have ranges? And that's where the continuous model comes in. So notice the difference here, fairly subtle, but this curve, if we would actually just trace the upper bounds of each of these discrete lines. So again, as we're looking at this discrete probability model, we're looking at just individual values, but when we switch over to this continuous, we're looking upon this continuum or interval at the bottom. So we don't have equally spaced discrete values, obviously. We're using a curve or a function. Now that curve can be represented as a function, and I'll show you what that looks like here momentarily. We're not going to really use it too much, but it's interesting, right? Okay, that describes probability density over the range of the distribution. So the higher the density, the higher the probability. Fairly easy to understand. Just know that the area underneath the curve is equal to 1, and just like discrete probabilities, all of them sum up to 1. Same thing. So we're talking about probability still. The normal distribution, aka the bell-shaped curve, interestingly enough, was called the bell curve because of blacksmiths. Interesting fact, a little tidbit for your knowledge bank that you're developing. Cool. Okay, blacksmiths would sometimes use a pile of dry sand. So if you would just pour sand into a pile, it looks like a bell, because that's what they used to create their casts for their molds for their bells. So the more you know. Okay, the normal distribution, let's continue on talking about a definition here. The normal distribution describes a special class of probability distributions, so we're still under probability, that are symmetric and can be described as two parameters. We can describe these things as the mean and the standard deviation, right? We've done this before with discrete, so it shouldn't be anything new. We're going to calculate these slightly differently, but the mean is the average density of our normal curve, and the standard deviation is the standard deviation of the distribution. Now, if we change these values slightly, so if we change mu or we change sigma minimally, you'll start to see how they affect the overall curve of the normal distribution. And here's a couple examples. So I have the mean being the same, but I'm changing the standard deviation. So smaller standard deviation means that the data is less spread out. That means it's very close together. Variation is very small. So if you look here, see what happens. So again, both of these have the same mean of 100. Okay, but we're changing the standard deviation. So if you lessen or shrink the standard deviation, we're going to get a much thinner curve, thinner bell curve. But if we start expanding that, then we're going to widen and flatten out this bell curve. So that's how the standard deviation affects it. Now let's talk about the mean. Okay, now this one I did sort of both of them, but the mean is very simple. The mean is just the middle. It's the line of symmetry for your bell curve, and that just shifts it on the x-axis. So horizontally, it'll just shift it left and right. And you can see again that the larger the standard deviation, the flatter that this bell curve gets, and the lower density across the board. So here's the properties of the normal curve. So if you can see the normal curve here in front of you. Just note a couple things, that we have inflection points at plus or minus the standard deviation. You won't really need to know those, but it's just nice to know because we have a downward cut and an upward cut that meet. If you've taken calculus or pre-calc, you're talking about curvature of lines here. So this is where the direction of the line shifts. Okay. So number one, this is the first property of the normal curve. The curve is bell-shaped. Crazy. With the highest point over the mean mu. So again, if we look back, we have our mean is right smack dab in the middle, and that's our highest point of the bell curve. Pretty easy to understand. Number two, the curve is symmetrical. Symmetrical. So if we go back, taking a look at our normal curve, if we split it in half at the mean, it is half and half. So 50% above, 50% below. So the curve is symmetrical about the vertical line through the mean mu. Okay? So those are two properties. So the mean is the highest point. It also causes us to have a line of symmetry in the middle. The curve approaches the horizontal axis but never touches or crosses it. So I want to go back to the picture one more time. And as you can see down here in the bottom, it's going to get very, 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 very close, but it's never going to actually touch. And if you're thinking about calculus, this is just the limit as x approaches negative infinity or positive infinity. We have this limit getting very, very close to 0, and it's approaching 0, but it never actually touches. Good to know. Okay. So the curve approaches the horizontal axis but never touches or crosses it. Okay, and the last property here is the inflection points that I talked about before between the cupping upward and downward occur at plus or minus 1 standard deviation. There's the bell you're about to show up in class. So I'm going to wrap this up really quickly. Here is the probability density function for each one of these, but we're not going to use it. We're going to end up using something called a z-score to estimate the probability underneath the normal curve. Okay, so next time what we're going to do is expand our idea of Chebyshev and transform it into the normal curve and talk about empirical rule. I will see you next time.